Myself, I'm Ganga Bhavani, Assistant Professor in EC Department. So today I would like to discuss the topic effect of feedback on amplifier characteristics, and also we shall see analysis of voltage series feedback amplifier. Okay. So before starting with understanding what is effect of feedback on amplifier characteristics, we shall define classification of amplifiers. Okay. So based on which signal is how the output voltage is varying proportional to the input voltage, we have different types of amplifiers. So those are voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. Okay. So voltage amplifier is an amplifier provides a voltage output proportional to the voltage input. That is, output voltage V0 is proportional to Vi. Okay, so output voltage is proportional to the input voltage, and the proportionality factor does not depend on the magnitudes of source and load resistance. Okay, so then amplifier whose output voltage is proportional to the input voltage, and at the same time the proportionality factor will not depend on the magnitudes of source and load resistance. Such amplifier is called as voltage amplifier. So next we shall see current amplifier. An amplifier which provides an output current proportional to signal current. Same thing here also. Output current is proportional to the signal current, II or IS if it is source. Okay. Then transconductance amplifier. An amplifier in which the output current is proportional to signal voltage. That is, output current I0. I0 is proportional to, so for this third case it is I0 is proportional to signal voltage Vi. That is, output current is proportional to input voltage. Okay. Then trans resistance amplifier, an amplifier in which output voltage is proportional to the signal current. That is, V0 is proportional to input current. Okay. Why we are calling it as transconductance amplifier? Because V is equal to IR or, okay now. So transconductance. So I is equal to 1 by R into V. Okay. So output current is proportional to input voltage, and proportionality constant is equal to 1 by R, which is generally taken as conductance. That is why we say that since I0 is proportional to Vi, since proportionality constant is a form of conductance, so you are calling it as transconductance amplifier. And here V0 is proportional to Ia. Generally what V is equal to I into R. So V0 is proportional to II. Here the proportionality constant is resistance. So what you are calling it as trans resistance amplifier. Okay. So based on the output proportional to the input, which factor of the output is proportional to the input, you have got four types: voltage amplifier, current amplifier, transconductance amplifier, and trans resistance amplifier. Right? Okay. Next, as we have seen already this block diagram in the previous class, but just like to revise. So in a feedback network, in a feedback amplifier, we'll have a basic amplifier whose gain is A, and in addition to that, you will be having a feedback network with gain beta. Okay. So generally the source signal is taken to be XS, right? Source signal is taken to be XS. So at the output of amplifier, basic amplifier, if the output signal is taken as X0, okay, X0 which is equal to input signal Xi into gain A. Xi into A will give you X0. Okay. So this output signal is given as input to the feedback network whose gain is beta. So the output of the feedback network is given by XF, that is feedback signal. XF is equal to this beta into X0. So XF is equal to beta into X0. Now this feedback signal is given, okay, it is given as input to the mixer. So in this comparator or mixer, the source signal and feedback signal are given. Here in this particular block diagram, you are adding the feedback signal with negative sign. So what you are calling it as negative feedback amplifier. Okay. So this difference XS minus XF is nothing but equal to your XI. Okay. So overall, the input signal is source signal is XS, right? Then output signal is X0, feedback signal is XF, and the difference signal between these two, XS minus XF, is nothing but your XI. Okay. So the basic amplifier here, it could be either a transconductance amplifier, voltage amplifier, current amplifier, or transresistance amplifier based upon the configuration, that is which signal is taken as output and which one is taken as feedback. We shall see all those 4 different types. Okay, so if you see in this first diagram, in this first circuit diagram, V0 is taken as output. Okay, so output is V0, and here you are adding the feedback signal in series with the source. In series with the source. So what the source is Vs. Okay, source is Vs. You are adding this in series, so source is Vs. So obviously the feedback signal Vf, feedback signal also will be nothing but your voltage signal Vf. Okay. So output is taken to be voltage. Voltage is given as input to feedback. So what output is voltage as well as input also is voltage. So what it is? Here the basic amplifier is voltage amplifier. So in voltage series feedback amplifier, the basic amplifier is voltage amplifier. Coming to the second case, current output is current. Okay, and here source is Vs. So this is again current. Output is current, so what it is current. Series source is taken to be voltage, so what it is series. So it is current series feedback amplifier. Current series feedback amplifier. So in current series feedback amplifier, output I0 is proportional to Vi. I0 is proportional to Vi, in which case, if you see the earlier classification, I0 is proportional to Vi. Third one, that is transconductance amplifier. Okay. So for current series feedback amplifier, the basic amplifier is transconductance amplifier. Now next one, if you see here, I0 is proportional to Ii. Okay. So output I0 is proportional to Ii. So what here the basic amplifier will be? Current amplifier. And what type of configuration it is? I0. Okay. Here source is also Is. Okay. When source is current source, definitely it is a shunt connection. Okay, and output is current, so what it is? Current shunt feedback amplifier. Okay, current shunt feedback amplifier. And this also, since the source is current, it is shunt configuration, and output is V0. So it is voltage shunt feedback amplifier. And here what can we observe? Output is voltage, V0 is proportional to Ia. So what type of amplifier, basic amplifier it is? Trans resistance amplifier. Okay, so generally in voltage series connection, this is voltage series connection. Okay, in voltage series connection, the basic amplifier is voltage amplifier. Okay, then current series connection, current series feedback amplifier, basic amplifier is transconductance amplifier. Current shunt configuration, basic amplifier is current amplifier. And finally in voltage shunt feedback configuration, what type of basic amplifier it is? Trans resistance amplifier is the basic amplifier. Usually if source is voltage, then it is series configuration. If source is taken to be current, then it is shunt configuration. And based on the output, whether it is voltage, if the output is taken as voltage, it is voltage series or voltage shunt. If output is taken, current, part of the current is taken as input to feedback network, then it is current series or current shunt. Again, depending upon the source. Okay. So totally overall, for current voltage series, it is voltage amplifier. For voltage shunt, it is trans resistance amplifier. For current series, the basic amplifier is transconductance amplifier, and for current shunt feedback configuration, basic amplifier is current amplifier. Okay. So coming to effect of feedback on amplifier characteristics. Okay. So in the previous class, we have seen how the what is the effect of negative feedback on voltage series configuration. That is, output impedance has reduced, input impedance has increased, and the voltage amplifier gain has been stabilized. Okay, and it has improved the characteristics of VRs. You can see here, voltage series it is voltage amplifier, current series it is transconductance, current shunt it is current amplifier, and voltage shunt it is trans resistance amplifier. So these amplifiers are used, and definitely the characteristics of these particular amplifiers will be improved by using the feedback. Okay, and we have also seen the gain feedback has been stabilized using negative feedback amplifier, and bandwidth has increased, and nonlinear distortion as well as noise have been reduced in case of voltage series configuration. Whereas this effect of feedback in different configurations is varying. Okay, it is quite different. It is not the same with all the configurations. Okay, always to have high output impedance and to have low output impedance and high input impedance, always it is preferred to use voltage series feedback amplifier only. Coming to current series, if we see, R0F is increased. Of course, RIF also is increased. Coming to the bandwidth increases and nonlinear distortion will decrease. So comparing voltage series and current series, the effect of negative feedback is same with respect to all other aspects except that the output impedance in case of current series is also increasing. Except this, the rest all are almost similar. Now you can see here what is the gain that is stabilized. In voltage series, you are taking the feedback gain with feedback as AVF. If it is the amplifier that you are using is transconductance amplifier, then the gain with feedback is taken to be GMF. If it is current amplifier, AIF. If it is trans resistance amplifier, it is RMF. Only thing, based upon the basic amplifier, we are defining the gain with feedback. If it is voltage amplifier, AVF, current amplifier, AIF, transconductance amplifier, GMF, because conductance is usually indicated using G. So GMF, and trans resistance amplifier with feedback, the gain is given by RMF. Okay. And coming to current shunt, output impedance is increasing. Okay. Whereas RIF, that is input resistance, is reduced. Right. Bandwidth increases and nonlinear distortion will decrease. And coming to voltage shunt, R0F decreases, RIF also decreases, and bandwidth increased and nonlinear distortion decreases. So on the whole, if we observe, bandwidth is increasing in all the cases by using negative feedback. Non-linear distortion is also reducing in all the cases. Okay. Only thing is, input impedance, it is increasing for series configuration, that is voltage series or current series. Input resistance RIF is increasing, whereas for current shunt and voltage shunt, RIF is reducing. And coming to R0F, output resistance with feedback, it is decreasing for voltage series and voltage shunt, and it is increasing for current series and current shunt. So this is the overall summary of effect of negative feedback on amplifier characteristics. So whether it is voltage series, voltage shunt, or current series, current shunt, you can see that bandwidth is increased as well as nonlinear distortion has reduced using negative feedback configuration. Okay. One, RIF increases for series configuration and decreases for shunt configuration. R0F, it increases for current series and current shunt and decreases for voltage series and voltage shunt configuration. This is the effect of negative feedback of amplifier characteristics. Okay. So next we shall see method of analysis of feedback amplifier. So the feedback amplifier is separated into two blocks, as we have seen, the basic amplifier and the feedback network. Basic amplifier, it could be any one of the four: voltage, current, or transconductance or transresistance amplifier. Okay. And the feedback network gain is given by beta. So with the knowledge of A and beta, we will try to calculate AF, that is gain with feedback, then RIF, input resistance with feedback, as well R0F, that is output resistance with feedback. Okay, now, so before that, if you want to, first thing what we have to do is we need to draw the basic amplifier configuration without feedback. To draw the basic amplifier configuration without feedback, we need to follow certain steps. What are those? First thing, if you want to find the input circuit, okay, a basic amplifier configuration without feedback, to draw it, what we'll do is first we'll draw the input part and then the output part. To find the input circuit, what we'll do, for voltage sampling, means if it is either voltage series or voltage shunt, what we have to do to draw the input circuit, we will set V0 equal to 0. We will set V0 equal to 0. That is the thing you have to follow. Suppose if it is current sampling, that is it is current series or current shunt configuration, then you will simply set I0 equal to 0. That is, you are opening the output load. Here you are shorting the output load. Okay. Voltage will talk with respect to nodes. So to find the input circuit, if it is voltage sampling, that is if it is voltage series or voltage shunt configuration, to find the input circuit, what we'll do? we will short the output node. That is, V naught equal to 0 is set. On the other hand, if it is current series or current shunt, then what we are going to do, we are going to set I naught equal to 0. That is, we are simply opening the output loop. So this is the thing to find the input circuit. Now on the other hand, if you want to find the output circuit, to find the output circuit, what you will do, we will set Vi equal to 0. Vi equal to 0 for shunt comparison. That is, shunt means what? It could be voltage shunt or current shunt. Okay. So for shunt comparison, we will set Vi equal to 0. If it is series comparison, we will set Ia equal to 0. So to find input circuit, okay, to find input circuit, if it is voltage sampling, then it is, we will set V naught equal to 0. If it is current sampling, we will set I naught equal to 0. That is to find the input circuit. If you want to find the output circuit, what we will do, if it is shunt configuration, then we will set Vi equal to 0. If it is series configuration, we will set Ia equal to 0. Okay. So this is the thing, only to these steps are to be followed in order to draw the amplifier, basic amplifier configuration without feedback. Okay, this is to find the input circuit and this is to find the output circuit. Then, if you want to analyze a given feedback amplifier, it could be voltage series, voltage shunt, current series or current shunt. If you want to analyze any one of the feedback amplifiers, then we need to follow certain steps. Okay, now, in that, first one is identifying the topology. That is, based on the what output is being sampled and what is the source, based on those given data, you should be able to identify the topology. Okay, that is, say if the feedback signal is XF, is a voltage or current. If it is voltage, if the feedback signal is voltage means source also should be voltage. Yes or no? Source also should be voltage. If the feedback signal is current, source also should be current. Okay, now, so if the feedback signal is voltage, then source is voltage means what type of connection it is? It is series connection. Okay, now, if feedback signal is voltage, then source also will be voltage. When source is voltage, what type of connection it is? Series feedback connection. Okay, and if the feedback signal is current, then definitely the source also will be current. Source is current means what type of connection it is? Shunt connection. Okay. The next thing is the sample signal X0 a voltage or current? Again, if the sample signal X0 is voltage, then what type of feedback network it is? It could be either voltage series or voltage shunt. If the sample signal is current, then it will be current series or current shunt. So based upon the feedback signal as well as the output voltage XF and X0, we will identify the topology, whether it is voltage series, voltage shunt or current series or current shunt. Okay. So if X0 is voltage, then it could be either voltage series or voltage shunt. If X0 is current, it will be either current series or current shunt. Similarly, if the feedback signal is XF is voltage, then it is series. It will be again voltage series or current series. If the feedback signal is current, it will be voltage shunt or current shunt. That is the way how you identify the topology. The next thing is, first step is to identify the topology based on XF and X0. Later what we will do, next step is we will draw the basic amplifier circuit without feedback. So just before we have discussed in the previous slide, that is these two steps, how to draw the basic amplifier circuit without feedback. Okay. So we will first step is to identify the topology. Next thing is we will draw the basic amplifier circuit without feedback using the two steps what you have discussed earlier, input circuit and output circuit. So once you have drawn the basic amplifier, so next thing what we will do is, if XF is a voltage, that is if feedback signal is voltage, then definitely the source also should be voltage. So what he is saying, if XF is voltage, use Thevenin source. Okay now. So if feedback signal is voltage, we will use Thevenin source. Thevenin source is nothing but voltage source. Okay. And if XF is current, if feedback signal is current, then we have to use current source, or simply you call it as Norton source. So third step is to choose the proper source based on the feedback signal. Fourth, replace each active device by the proper model. So once you have drawn the basic amplifier circuit and you have identified which source is to be used, then what we have to do, we have to replace the active device. Basically, we will be analyzing transistor amplifier circuits. So next step is you need to replace that active device by its proper model. If you are trying to analyze at higher frequencies, you'll replace the transistor by hybrid pi model. Hybrid pi model. If you are using the transistor if you are trying to analyze it at low frequencies, then you'll be using H parameter model. Okay. So transistor at higher frequencies can be analyzed using hybrid pi model, whereas transistor at low frequencies can be analyzed by using H parameter model. So fourth step is to replace the transistor or to replace the active device by its proper model. It could be either H parameter model or hybrid pi model based upon our understanding. In our class, we'll try to analyze at lower frequencies. That is using H parameter model. Okay. So fourth one is to replace the transistor by its equivalent H parameter model. After that, fifth one is you will calculate beta. Okay, using XF and X0, you will calculate the value of beta. XF beta is nothing but feedback signal by output signal, that is XF by X0. You will find out beta. After finding beta, sixth step is to find out A, that is gain without feedback. Sixth step is to find out A. So once you get A and beta, finally you will find out all these factors: desensitivity, gain with feedback, RIF, R0F, and finally R0F dash. Okay. So overall, what are the 7 steps that we are supposed to follow? First thing was to identify the topology. Then second one, after identifying the topology, what we are supposed to do? We will draw the basic amplifier circuit without feedback. Input circuit and output circuit. Then based on the feedback signal and output signal, we will identify, based on the feedback signal, we will identify what is the source to be used, whether it is Thevenin source or Norton source. Then we will replace the active device by its H parameter model. Okay. Then fifth step, we will calculate beta. Sixth step, we will find out gain without feedback A. And finally, using A and beta, in seventh step, we are going to find out all other factors like D, AF, RIF, R0F, and R0F dash. Okay. You can just have a quick view in this table. Okay. Feedback signal is XF. For voltage series and voltage shunt, okay, feedback signal is XF. Yeah, feedback signal for series connection it will be voltage, and for shunt connection it will be current. Sample signal X0, for voltage series and voltage shunt it will be voltage, current series and current shunt it will be current, obviously. Or based on the sample signal X0, if it is X0 is voltage, then definitely it is either voltage series or voltage shunt. If X0 is current, it will be either current series or current shunt. So to find the output loop, to find the input loop, what we are doing? To find input loop, we are setting, if it is voltage connection, to find the input loop, what we are doing? V0 equal to 0. Okay, V0 equal to 0. We will set V0 equal to 0. Okay, for voltage sampling. And for current sampling, we will set I0 equal to 0. And to find the output loop, we will set Vi equal to 0 for shunt connection. And for series connection, we will set Ii equal to 0. Okay. And what is the source that we are going to use? If it is voltage series, okay, voltage series or current series. That if it is series connection, then we are going to use Thevenin source. If it is not shunt connection, we are going to use Norton source. It will depend upon the feedback. Okay. So if feedback signal is voltage, then you are going to use Thevenin source. Feedback signal is voltage, then you are going to use Thevenin source. If feedback signal is current, you are going to use Norton source, as we have seen in third step. Okay. Then finally we'll calculate all this for each configuration. Okay. While analyzing each configuration, you will see what will be the values of beta, A, D, AF, IF, RAF, R0F, and R0F dash. Okay. So first, if you see, beta is equal to XF by X0. Okay. So based upon what is the feedback signal and XF and X0, you will have the values of beta. A, what is A? X0 by Xi. X0 X by is cancelled. Once you get beta and A, D is given by 1 plus A beta. Okay. Then you will find out AF. AF is nothing but A by D. That is A by D. So A by D in each case is calculated. Here it is AV by D. Here it is GM by D. AI by D and then RM by D. That is AF. RIF is, see, input impedance is multiplied by D sensitivity. So RIF equal to RI into D, and here it is RI by D and RI by D. For current shunt and voltage shunts, yeah, as we have seen in the earlier, RIF will increase for, yeah, just see this, RIF will increase for series and decrease for shunt. Okay, RIF will increase for series and decrease for shunt. So what you see, RIF, it is increasing for voltage series and current series. Okay, if you see, it is multiplied by D for voltage series and current series. Whereas for voltage and current shunt, it is divided by D, that is, it is going to reduce. Okay, now coming to R0F, R0F will increase for current series and current shunt. It will decrease for voltage series and voltage shunt. Right. Finally, R0F dash is given by R0 dash by D. This is R0 dash into 1 plus beta Gm by D. We will try to calculate all this. Okay. So out of all this, first we will study today analysis of a voltage series feedback amplifier. Okay. Voltage series feedback amplifier. We will try to analyze voltage series feedback amplifier using all the steps what we have discussed earlier. Okay. So in voltage series feedback amplifier, the basic amplifier that you are going to use is voltage amplifier only. As we know, output is voltage as well as input also is voltage. Output voltage V0 will be proportional to input voltage VI. That is, basic amplifier is nothing but voltage amplifier. Okay. So consider this emitter follower circuit. Okay. Emitter follower circuit is nothing but it is a transistor is here. The transistor is connected in CC configuration, that is common collector configuration. Okay, here if you observe, input source is given to base through the source resistance RA, and output V0 is taken across emitter terminal. Okay, output V0 is taken across emitter terminal. Okay, and through collector you are giving RC and it is given to minus VCC. Right, this is a circuit diagram of emitter follower. Okay, so now. So first step is to identify the topology, right? To identify the topology, what is the output that what part of output is being sampled here? Output voltage is being sampled. So what it is voltage? Again, it could be series or shunt. And what is the source that you are using here? Voltage source. So voltage source is voltage, means definitely the feedback signal also will be voltage. Okay, feedback signal also will be voltage. So output X0 equal to V0 and XF also is equal to V0. XF also is equal to VF. So both are voltage. So what you say that this is what type of topology it is? Voltage series feedback amplifier. Voltage series connection. Okay. So once you have identified the topology, it is voltage series feedback configuration. Okay. Second step is what? After identifying what type of topology it is, next what we are supposed to do? We are supposed to draw the basic amplifier circuit without feedback. To draw this basic amplifier circuit without feedback, so what we have to do? What is our step? If it is voltage, if it is voltage sampling, what we'll do? We will set V0 equal to 0. Okay, we will set V0 equal to 0. If V0 equal to 0, okay, if V0 equal to 0, V0 equal to 0 indirectly, what does it mean? This is nothing but a short circuit. That's all. If V0 equal to 0, this is nothing but short. Okay, this is short mean. So what happens? If V0 equal to 0, what will be the input circuit? Simply replacing this by short. So whatever is left over, Vs, Rs and base to emitter, then emitter is given to ground. This is what the input part. Up to here it is the input part. What we are doing here, simply setting V0 equal to 0. V0 equal to 0 mean indirectly saying that this can be represented by short circuit. So what this will be the input part. It is redrawn as it is. Okay. Then if you want to draw the output part. To draw the output part, output circuit, what are we doing? We are seeing whether it is shunt comparison or series comparison. Okay. We are seeing whether it is shunt comparison or series comparison. If it is series comparison, what we are supposed to do? Since it is series comparison, we are setting II equal to 0. Input, that is II equal to 0. Okay. Since the output XF is voltage, since it is voltage sampling, to draw the input circuit, we have set V0 equal to 0. And since it is series comparison or it is series connection, we are setting II equal to 0. If it was a shunt connection, we would set Vi equal to 0. Since it is series connection, what we are doing here, we are setting II equal to 0. If II equal to 0, here if II equal to 0, that is if input current is 0, what does it mean? It is simply nothing but open circuit. When the current through a loop is 0, it means this is an open loop. If this is an open loop, whatever is left over, that will be the output circuit. So the collector, then resistance RC, see here, collector, resistance RC. After RC, you are giving this RC. RE is left over, no? RC, this negative terminal of RE is given here, RE, and then to emitter. Again, it is given to this part of the circuit is drawn here. RC is given to minus VCC is nothing but ground, that is this terminal. Then this RE, and given to emitter. This is how you draw the output circuit. So to draw the input circuit, since it is voltage sampling, we are setting V0 equal to 0. V0 equal to 0 means this is nothing but the short circuit. Then this will be the input circuit. Then to draw the output circuit, what are we doing? We are just setting II equal to 0. Why are we setting II equal to 0? Because it is series connection. Okay, since series comparison is used here, we are setting II equal to 0. II equal to 0 indirectly means that this input loop is open. If this is open, the leftover part of the circuit will become your output circuit. Okay, so finally, by using the two steps based on the sample signal as well as based on the connection, whether it is series or shunt, based on these two factors, we are drawing the basic amplifier circuit without feedback. Okay, that is how we draw the basic amplifier circuit without feedback. Then, so that was the second step. And third step, it is understood to use source, Thevenin source or Norton source. As usual, already it is given that it is voltage source. So it is voltage series feedback amplifier. And after finding the source, finding out the source, what are we supposed to do? Then fourth step is to replace the transistor by its H parameter model. Okay. Usually, H parameter model of a transistor is given by, if it is common emitter configuration, it is given by HIE, then a voltage source. Okay. And then this will be H0E. And this is V0. Okay. And this will be Vi. Right. This is HRE into V2. Okay. HRE into V2. And this is HFE into I1. Okay. V1. This is V1 and this is V2. This is actually the H parameter model of a transistor in CE configuration. But while analyzing feedback amplifiers, what we'll try to do is, we will try to replace this transistor by approximate H parameter model. To draw the approximate H parameter model, usually we will, to draw the approximate H parameter model, we ignore this HRE into V2 and H0E. So, neglecting this HRE into V2 and H0E, the approximate H parameter model of a transistor in CE configuration will be like, this will be HIE, okay, and then right. So, this will be V1, this will be V2, okay, this will be HFE into I1. Okay, so this is going to be the approximate H parameter model for. Now with this has reduced to common emitter configuration. Okay, now so replacing this transistor with approximate H parameter model, that is fourth step. Try to see this. Vs source is written as it is, then Rs. Okay, then from base, now this transistor. Okay, here input is nothing but base terminal. So this will be Vi. Vi is nothing but Vb, and this will be HIE, HRE into V2. Okay, so you have neglected that. So simply you have how is this input part? What do we have? We just have a HIE. So from after the RS, we are going to replace this transistor by this approximate H parameter model. So after RS, you are connecting this HIE in. So from RS to this transistor, that is RS in series with HIE. Okay, series with this HIE. After this, output side, what are we going to do? HFE into I1. See, here input is nothing but base. So I1 is nothing but IB. So we are writing here HFE into IB. Current source, then output will be left over. Output will be same. Between collector, this transistor is replaced by this part in the output. Okay, after this, the rest will be same again. RC and RE. Output is taken across this emitter resistor R. Okay, we are just replacing this transistor with this approximate H parameter model. Okay, so replacing this transistor with approximate H parameter model, this circuit amplifier, basic amplifier without feedback, is going to be reduced as this one shown in figure C. Okay, we are just trying to replace this this transistor with this approximate H parameter model. Then this is going to be the resultant. Okay, so with this resultant figure, we are going to find the remaining values. Now, so next fifth step is to find out the value of beta. If you observe here, the output signal X0 is nothing but V0. Okay, the feedback signal also is taken across the same resistor RE. So feedback signal VF is equal to output signal V0. That is VF is equal to V0. Then what is going to be the value of beta? Beta is equal to output signal V0 by VF. Okay, since beta equal to V0 by VF, it is given by equal to V1. So beta is equal to 1. Beta equal to 1. Okay, now since RS is considered as part of the amplifier, we have Vi equal to Vs. Okay, Vi is equal to Vs. Now coming to this first, we have calculated beta. After finding the value of beta, what are we going to do? We need to find out the gain without feedback. AV equal to V0 by Vi. Okay, if you just see in this previous circuit, for this one, if you apply KVL to this part, to this input loop, what do you get? Vs equal to, what is the current flowing through that? IB into RS plus HIE. Okay, so Vs equal to IB into RS plus HIE. Similarly, if you apply KCL to this output side, what are we going to get? V0 equal to, tell me, V0 equal to, what is the current flowing through this? HFE into IB. So V0 equal to HFE IB into RE. HFE IB into RE. Okay. So these are Vs and V0. Vs equal to IB into RS plus HIE. Vs equal to IB into RS plus HIE. And what is V0? V0 equal to HFE IB RE. HFE IB into RE. So these two values of V0 and Vs. Right. So V0, AV equal to V0 by Vi. Okay. That is equal to, what is V0? HFE IB into RE by Vi is equal to, as we have taken Vi equal to Vs, Vi equal to Vs. If we simplify this further, HFE IB into RE by, what is Vs? Vs is nothing but equal to this one, IB into RS plus HIE. Okay. So cancelling this IB, we'll have HFE into RE by RS plus HIE. Okay. So gain without feedback, AV is given by AV equal to HFE into RE by RS plus HIE. Okay. So to find out the gain without feedback, we have taken AV equal to V0 by Vi. Okay. And the values, expressions for Vs and V0 are taken from this C diagram, C circuit diagram. Okay, applying KVL to this First loop will get Vs equal to IB into Rs plus HIE, and V naught across RE is given by V naught equal to the current flowing through this outside loop is HFE into IB. So HFE IB into RE. So these are the expressions for Vs and V naught. Taking these expressions Vs and V naught, we are just substituting in this expression AV equal to V naught by Vi. It is nothing but equal to V naught by Vs. So V naught is HFE IB RE by what is Vs? IB into Rs plus HIE. So on simplification, we'll get AV equal to HFE into RE by Rs plus HIE. Okay. After finding AV, the next step we are going to find out D, AVF and all. So D is equal to what? One expression for D sensitivity is 1 plus beta into AV. Okay, 1 plus beta is equal to 1 as we have seen. AV is HFE RE by Rs plus HI. So if you simplify this, you'll get on cross multiplication Rs plus HIE plus HFE RE by Rs plus HI. This is the final expression for D. D equal to Rs plus HIE plus HFE RE by Rs plus HI. Okay. After finding D, we'll try to calculate gain with feedback. Gain with feedback, as we know, using negative feedback amplifier, gain with feedback is reduced by a factor D. So AV by D. Gain equal to AVF equal to AV by D. So AV we have seen in the previous step. What is AV? HFE RE by Rs plus HIE. HFE RE by Rs plus HIE divided by, and what was D? Rs plus HIE plus HFE RE. HIE plus HFE RE by, what was the denominator? Rs plus HIE. Rs plus HIE. So if you cancel the denominators on both numerator and denominator, you will get HFE into RE by Rs plus HIE plus HFE into RE. So this is what the final expression for gain with feedback is equal to HFE into RE by Rs plus HIE plus HFE into RE. So this is how you calculate gain with feedback. After finding AV and D, simply AV by D gives you gain with feedback. And in this expression, if you see, if HFE into RE is far greater than Rs plus HFE, if this factor is far greater than this one, then we can ignore this. In such case, what will happen? Okay, so HFE RE by HFE RE. So in such case, AVF will be approximately equal to 1. That should be the case for emitter follower. Okay, so then we'll try to see the input resistance without feedback. Yeah, input resistance without feedback, if you see from this circuit diagram, RI equal to input resistance will be what? RI input resistance from this cell. RI will be equal to Rs plus HI. So RI is given by Rs plus HIE. Okay. So input resistance with feedback is given by RI into D. So Rs plus HIE into D is what? Rs plus HIE plus HFE into RE by Rs plus HIE. On simplification, you will get, cancelling these two factors, you will have Rs plus HIE plus HFE into RE. That is RIF. That is input resistance with feedback. Okay. And R0 dash is equal to that. You can see from this circuit diagram. Yeah. R0 dash is nothing but looking into this terminals, it is equal to RE. So R0 dash is equal to RE. R0 dash is equal to RE. Finally, we'll try to find out the output resistance R0 F dash. R0 F dash is equal to R0 dash by D. So this is equal to R0 dash is how much? RE. And 1 by D. D was equal to Rs plus HIE plus HFE RE by Rs plus HIE. So when you take 1 by D, we'll just take the reciprocal. So R0 F dash equal to RE into Rs plus HIE by Rs plus HIE plus HFE into RE. We're just substituting the values of R0 dash and D. Finally, R0 F equal to limit RE tend to infinity R0 F dash. Okay. So limit RE tend to infinite. What is R0 F dash? RE into Rs plus HIE by Rs plus HIE plus HFE into RE. So what are we going to do now? We'll just write the same limit RE tend to infinity. Okay. RE into RS plus HIE by, I'll just try to take RE common in the denominator. Okay, if I take RE common, I'll get RS plus HIE by RE plus HFE. Okay, so what happens now? We'll just cancel these two. Limit RE tend to infinity RS plus HIE by RS plus HIE by RE plus HFE. Now if we substitute the limit RE equal to infinity, something by infinity, this factor is going to be 0. So what do you get? RS plus HIE by HFE. Okay, this is the final expression for R naught F. Therefore, R naught F is equal to RS plus HIE by HFE. Okay, this will be the final expression for R naught F. RS plus HIE by HFE. Right. So this is how we analyze the feedback amplifier with feedback. Feedback amplifier. There is voltage series feedback amplifier. Right. So first we have identified the topology. Next step we have drawn the amplifier circuit without feedback. Then third step we have identified the source. Then replacing the active device with its approximate H parameter model. Then we have calculated the values of beta, AV, and using beta and AV we have finally reduced the expressions for desensitivity, then gain with feedback, then RIF, then R naught F dash and R naught F. Right. So these are the references that I've used. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.